Right, so today we are going to learn about hardness removal. So we'll learn about what is hardness, how to define it, how to measure it, how to estimate it, and then if you know your water has lots of hardness, how to remove them. You'll also learn what hardness cause, what kind of problem that hardness may cause in your water distribution system. So just to remind, this is the last class of that relevant for midterms. So anything beyond today's is not part of the midterms. And because this class is also not cumulative, you will not be asked the questions that is already asked in the midterms, as far as long questions are concerned. Short question you may be asked because they will keep coming back in the same fundamental for different applications. For instance, BOD will come back again in wastewater treatment plant, so that means BOD short question can be also relevant. But as far as long questions, everything that you cover until today will not be part of the finals, but only part of the midterms. Just to give you again reminder, homework 4 supposed to be due on Friday midnight, but you have grace period for until Monday to submit. We don't have to ask for extension. It's already granted for that grace period. Homework 5 will be released later today. The reason I want to release it today is because I want to give you opportunity to work on it as long as you can, so that you have opportunity to ask those questions for midterms. And quiz 2 will be next week on Wednesday. The same format. You'll have 24-hour windows to answer the questions, but the window will be 20 minutes. The same, like very similar to last time. And also quiz is not cumulative. That means everything we asked in the last quiz will not be part of this quiz. So that's why lecture 5 to 8 are relevant. Everything this week is not part of the quiz. Um, Again, I just realized that we don't have office hour most of the time, even though my intention was to have office hour at the end of this class. So for now, this week, I set the time on Thursday, 3 to 4 p.m. It may not work for many of you. I don't know because I didn't ask what time. It just happens that this week I'm available that time. But just know that if you have difficulty and you want to meet me, you got to send me email because I can meet any other time just with you. So I'm available if you ask me when you if you want to meet. Um, so there is a question on repeat on quiz. So again, lecture 5 to 8, those are part of the quiz. So that means week 3 and 4 will be part of the quiz. Week 1 to 2, we are already tested in the first quiz, so that's not going to be part of it. Um, the homework is due next Monday. Yes, the homework 4 is due on Monday. Um, that means what I'm saying is this is extension period. Without, you don't have to email me to asking for extensions. If you change the submission window grace period so that you, even you submit, it will not be considered late. And typically I don't take any points off for late submission as long as you ask for extension. And usually I never really deny extension. Obviously, if somebody asks me 10 times extension in 13 week, obviously that's something issue we have to think of, but rarely that's the case. So that's why never not submit. Always ask if you're struggling for any reason. Okay, so office hour tomorrow, same link, Zoom link. So I'll be available on Thursday, tomorrow at 3 p.m. Let me just double check if that's the one I intend to write. Office hour, yes, 3 o'clock. And again, I have nothing to discuss in the sense I'll be there just with any question you ask. You can ask about class materials or just to share your concern about how class is going. How do you feel about it? So that's kind of a feedback process. So I'll be happy to see some of you if you want to join. But just know that if you can't join because of you have other class that time, you can always meet me any other time. Just send me an email or post on. I prefer always campusware because that's where a lot of students can also see. So that way we can see which other time will be good for many students. This is just for this week. Next week we'll decide another time. Um, Again, this is what we are going to learn is on the chapter 6. That's the very like 4 or 5 page in after 300, page number 300 in section 4. So we'll learn about that today. We'll learn more specifically about hardness and alkalinity. And these are the two concept or parameters, water parameters people measure, because it tells about water quality. It also says something about what your water can do. And just to know that this is not a contaminant, this is just a natural property of water. It means how much minerals you have in it and what those minerals can do. So we'll learn about hardness. We'll learn about alkalinity because that's related to how to treat hardness. And then you also learn how what's the source of alkalinity. And you should also learn what's the difference between soft versus hard water. Just to show you here the example, soft water means you can create lots of foam when you wash detergent or you put detergent in it. But if you have hard water, the detergent will not make that kind of foam. Why it is important? That means your if you're cleaning your cloth, all those foam things will not be removing your dirt. It's going to stick on your surface. So that means if you take shower using a foam or anything, that also stick on your skin. So that's why it's very important to know uh, if you have hard water. And we also will learn about total hardness, carbonate hardness. We'll learn about all the definitions. At the end, we'll also learn how to remove hardness. And so we'll understand the chemical reaction behind this water softening, means removing hardness. All that you learn today. So it's a very simple concept, hardness and alkalinity. Alkalinity is very small part of the class, but hardness is everything about this class. Um, let's think of alkalinity. What is alkalinity? So as you see, if I ask you to measure water quality properties, a lot of times you measure pH. Sometimes people measure conductivity, um, means how much ions there. Okay, pH is mostly how much H plus ion there. Okay, conductive means how much all ions. Okay, what about alkalinity? Alkalinity is related to pH. It means how much ions that can. So I'm just going to write alkalinity. All you're asking is how much ions there in the solutions that can either um, remove a protons, remove H plus, or donate H plus. Okay. So why that means? Because alkalinity is related to pH or buffer capacity of a system. So in nature, pH can change a lot of reactions. So if you have certain type of ions, that will prevent those pH to change when you are acid or base. So that's all about alkalinity. So that's why the definition of alkalinity is just a measure of water capacity to absorb hydrogen ions without significant pH change, because that it's kind of remove them from the system, so the pH is not effectively changed. So the alkalinity is the unit is moles per liter. It's like a mole because any ions is a moles per liter or milli equivalents of liter. So let's think of what are the different ions there. This is the formula, but this is not the complete formula. So let's write about what I just said. I say any ions that can remove hydrogen ions from the system. So if you think of SCO3, what it can do is it can take one protons and it become H2CO3. Okay. So what does that mean? So if you have lots of this bicarbonate, which is SCO3, when you add the acid which release this proton will not be there to react with anything because this bicarbonate will take it out. So that's the reason it can control the pH. It doesn't make the pH increase even you are adding protons. So let's think of the second ions. This is carbonate. Usually it can take two protons because it has two charge, S2CO3. So that means it can take two protons. So if you have one carbonate ions, it can take two protons. So that's why there's that term 2 is here, okay, because it can take that two protons. Same thing, naturally every water has OH ions and so that can take one protons and become water. Okay, so what I'm saying here is that if you know how much bicarbonate, how much carbonate, how much OH, you kind of know how much protons they can take. Okay, and but then you have to account for that there is some amount H plus already present in water, so you have to subtract them because they will these will react with that H plus already there. So you have to first account for those H plus. So that's why you have a subtractions. So what that means is this is the amount of H plus ions, of the capacity of the system to remove this much H plus ion. Okay, so that two factor is because of the two charge. And so now you may ask question, is this the only ions present? Not really. You can add, let me say, you can add SO4, any kind of acid, one dissociate that can have something, but these are so strong acid, they are not stable. So in nature, um, you can add all these things, any ions with negative charge, as long as they can take protons. But these are the most common one and has also extremely high affinity for H plus. So that means they are more likely to take H plus than other ions. So on practical purpose, we always try alkalinity is this much. So that's the only concept. So now if I ask you to measure alkalinity, all you have to do is measure these concentrations and add it up, moles per liter, because you can add milligram per liter because they are not same units. So you have to change to a unit that's equivalence. So moles per liter you can add, or you can change to normality, which is mill equivalents per liter. So this is milli equivalents per liter, and equivalence liter is normality. Okay. So most of the time you just do moles per liter. Okay, a lot of times you can change one unit to another. You already learned that in this class before. So now, in most of the time in nature system, let's think of what would be the alkalinity, because in nature this concentration can change. So let's start with the real nature. In most of the groundwater, if you think, the pH is between 5 to 8. Okay, to think of surface water or groundwater, it's always around that range, 5 to 8. And it turns out within that 5 to 8, there is not all these species are equal concentration. There are some species which has much higher concentration than other. And it turned out, if you see within that, this is the concentration of bicarbonate is way order of magnitude more than the other concentration. If you see this is S2CO3, that doesn't matter because that's not part of the equations. Look at this one. If you take this particular point, pH 8, the CO3 concentrations is 2 order of magnitudes smaller than SCO3 concentration. That means it's 1,000th of how much you'd expect in SCO3. So that means you can always neglect this one at pH. So at pH around 5 to 8, you can say that SCO3 is much higher concentration, 3 order magnitude concentration than SCO3 carbonate. So that means you can neglect these concentrations towards zero. It's not zero, but it's very small compared to the other one. And think about that pH versus the OH ion concentration. So the OH is this one. This is OH. This is H plus. So now look at this. At that pH, OH is even much smaller. Okay. So that means you can also neglect OH. And look at the H plus. At that pH, H plus even way smaller. Okay, so that means you could say that if you're adding this a large quantity with a very tiny amount, you're not going to change the amount. So that's why at that pH, if you are measuring alkalinity, you can almost assume that this is equal to the concentration of SCO3. Okay, because that's the most stable species at that pH. So why it is important? Because when you do carbonate or the hardness analysis, a lot of times you are given alkalinity. That means you know the concentration of this one. Okay. So if somebody gave you alkalinity, you know what's the concentration of HCO3. And HCO3 is a very important species for hardness calculations. All right, so now that we learn what we learn, so let's see a questions, what we learn. You added 10 millimoles of sodium hydroxide to a solution. What would happen to alkalinity of the solutions? So there is no D, so don't submit any questions on D. You can submit A, B, C. And again, I'm just going to write alkalinity equations. I'm going to switch it little here. Look at the alkalinity equations. That's this plus this plus this minus this. Okay. And you're adding NaOH. So when you add NaOH, you're essentially adding sodium and hydroxide. So now you have to see whatever your alkalinity before, is this going to increase or decrease? Again, alkalinity, I'm just going to write the equations. SCO3 minus. That's the alkalinity equations. Now that you know, should be able to answer this question more effectively. Okay, I'm going to end the poll just to show you how much percentage. So share the results. 70% says this one, 19% says this one, 9% says this one, 1% accidentally pressed D. So now let's see what the question was. The question was, if you add sodium, 10 millimoles of sodium hydroxide. So when you add sodium hydroxide, you are adding OH ions. If you're adding OH ions, this OH ion, this is increasing. That means alkalinity has to increase. So the right answer is increase. So anytime I ask a question, you just have to see what's the equation. Am I adding any of the species? If you're adding H plus, obviously alkalinity will go down. So if your H plus is increasing, that means alkalinity will decrease. Okay. Same thing. Just look for any equation that's not part of the equation that doesn't change alkalinity. All right. Let's see how much you learned. So I'm going to stop sharing this one. I'm going to ask again these questions, but it's a little tweak here. You add 10 millimoles of sodium chloride to the solution. So you add NaCl. That's basically Na plus Cl minus. And I ask you what would be the change in alkalinity. So again, alkalinity is, I'm going to write the equation again, SCO3. It's going to concentrations. This bracket means I'm asking about concentrations. Okay, I'm going to end the poll in a few seconds. You have 7 seconds. So again, whatever comes to your mind, you should answer, because there is no, I'm not expecting here you get everything right. I'm not even looking at who is getting what. All I'm looking at is how much percentage. Okay, so I'm going to end the poll now and share the results. Okay, 70%, the distribution doesn't change. 23%, 7%. Okay, let's think of this way. Alkalinity, I'm asking how much alkalinity will change if you add this one. Look at the sodium. There is a sodium in this entire equations. There is none. That means it doesn't take the hydrogen ions or it reacts with hydrogen ion. The chlorine, you have equation here, chlorine. No, that means chlorine cannot really take H plus ion. It doesn't have that strong affinity. So that means, none of these things would influence the equations. So that means, if you add any of these, because these are not in this equation, you can say that this doesn't change at all. So it's no changes. So the right answer is C. So that's the typical quiz questions in the midterms or the short questions. So you should think of all that. That's the only thing you have to learn. All you have to learn is alkalinity is all about the buffering capacity, and it has equations. All you have to look for is does the equation changes if I add certain species, and whatever you added, that changes alkalinity.
Professor,
Yeah.
quick question. In that previous example, what could the alkalinity change if there was some other compound that was present in the solution before? So say there was a higher concentration of just dissociated like hydroxide ions, could the sodium react with that and then take those dissociated ions away?
Okay, that's a good question. The question was if you're, it may not be directly present in the solutions, but does this ions take out some of which is already there, right? So let's say what am I saying is, what if this sodium is taking away some of the OH and become NaOH? That means it's decreasing alkalinity because it's taking away OH. So now you have to think of, is this going to happen? Um, well, that for to understand that you have to think of what's the weak acid and a strong base. So NaOH is a strong base, means it has high, it is much easier to dissolve or break it into OH ions. So that means the reaction NaOH is going to become Na plus OH minus. So the thermodynamics of the, because it has very high solubility, it is going to go back to Na plus and OH minus. And in the normal circumstances, it's very difficult to bring it back to precipitate. So this is more likely the reaction. This reaction, this type is not possible. Because for that to happen, you have to have way more OH ions and Na plus to exceed that solubility limit. And in normal circumstances, that's not going to happen. That's why even Cl, if you know HCl, that's a hydrochloric acid, that's a very strong acid. It becomes Cl minus and H plus. So this is possible, but to go back this side, it's not possible unless you have way more H plus and chlorine, which is not the case in any natural systems. That's why you don't go back in that directions. So anything strong acid and strong base, they will not form in the reaction. So NaOH, HCl are very strong acid and base. So for this class, I would say that do not think of too over complicated things like this. The reason is I have not taught you anything about what is strong acid and strong base. Just for this class purpose example, you just have to check if any of the species changes directly. I'm adding it or not removing it by direct. Did I say any reaction that will do it? If not, then if not. Okay. But it's a very good questions because that's how the real chemistry behind these equations. Why we didn't put any other terms like Na plus here. Okay, any other questions on alkalinity?
Kind of just want to tack on to her question, so we don't have to worry about like if it's going to make a precipitate or not. Then
Is this a question you are asking?
just kind of wanted to confirm that we don't have to worry about like
Yeah, it's not going to
if
precipitate. Yes, it's not going to precipitate because the solubility of NaOH is extremely high. So you need way high concentration of sodium and OH. The amount I added here is very small. I didn't say that add tons of sodium chloride. Okay,
okay.
that's very low concentration. That's why I didn't say. I mean, obviously, at some point there will be precipitation, but for that to happen, you have to add so much salt. Okay, so now we get to the main topic of this class, hardness. So when you think of what is hard, you are not thinking of as a physical mean like this is really so hard. It's like this is what is a liquid. It can't change its density that much. But there is a reason why it is called hard water. The reason is if you have to think of the history of how hardness is discovered. So a long time ago when we are supplying water, you pump water from ground and then this is a tube. Okay, this is this pipe or tubes. That's what you supply water. And over time, what people notice that over time when they are supplying this tube, if I take the tube here, like this is the tube, this is the original starting point, then that you have kind of scale build up. Okay, scale build up, and then over time it's going to build up like this. Okay, so um, these these are the scale that build up over time, and you have to wonder why this is being so much scale here in some water compared to other water. And that's the reason they call it hard water, because you create this, this hard core in the surface in the pipe. So this scale, the reason this scale developed is because of your water is hard water. And so you have to think, what is the scale made up of? Okay, that scale made up of salt. Okay, that salt is mostly calcium, magnesium. I'm just going to add few more. Um, so and then you have other ions like CO3. So these are positive charge, and then the negative charge, because when you create salt it has both positive and negative. So it could be SO4, it could be CO3. um, I'm looking for something like more common which is present in nature. So sulfate, carbonate could be another thing. I didn't write chloride because chloride is extremely soluble. If you take magnesium chloride, they are very soluble. They are not going to form precipitate at the normal conditions. So what I'm basically saying, you are building up this scale, and those scale is formed. This carbonate, sulfate, they are naturally present in every water, but this ion, positive ion, they usually stick with everything in nature. So that means if you have a lot of those, so that could be the hard water. So most of the time when you think of hardness, that's because you are asking how much of this positively charged ion. And if you notice, I didn't write sodium plus or potassium plus. These are not cause of hardness. The reason is plus ions are not very extremely, they don't have that much affinity to these ions and to produce precipitate. They are extremely highly soluble. So when you think of hardness, you are mostly looking for any kind of cations, means positively charged with 2 plus or greater charge. Okay, so think of more like a, I remember this more like a, the lane, faster lane where you have two or more person has to be there to drive that roads. So same thing here. If you have to have more than 2 plus charge, 2 or larger charge to build up this scale. So basically, when I'm talking about hardness, I'll think of that positively charged ions. And you are just calculating the sum of that ion. So you already know the units. You know how to add it up based on in different units, and that's all about hardness. Okay. So the theory, that much you already know. And now it's about applying that in the concept. But let's think of a little bit, take a pause, and why even we bother. Yes, pipes are important. We can replace the pipe, but most of the time it has also unintended consequence on your skin as well as on your hair. The reason, as I said, hard water has lots of positive charge. Plus calcium, let's say magnesium 2 plus or calcium. And and it can precipitate. And so let's say we take all the, we are using shampoo or using whatever the body wash that you have, it has surfactant. The body wash usually create foam, right? And that foam surfactant usually negatively charged. So I'm just going to write um, negative charged ions from soap. When you dissolve soap, the foam that produce, it has negatively charged ions. So this negatively charged can react with this one and they precipitate. So that means if you're taking a shower or using your soap in a hard water, it's going to create this kind of coating layers of this soap, and that will dry the skin. When you even you take if you wash your body many times, still there will be very fine coatings that you will not see. So that's why you will develop the skin rash, because skin cannot breathe. There are a lot of other issues that can happen. And then also you can see your hair is kind of sticky. So that's basically every time you have this itchy skin or anything, that maybe you're using hard water. So that's why it's very important to remove this hardness before distributions. And again, just to what we discussed, these are the evidence. You can see this scale. You can take your, if you look at your the faucet or the tap in your bathroom, particularly the location where you use warm water, because the warm water, it has more likely to precipitate when you change that temperatures. So it's basically you're looking for the scale. Wherever you see a lot of the scales, that means you have some hard water. Again, these are not dangerous, so you don't want to be alarmed, but it should be some amount hardness. Hard water is good actually, because it create that coating and that will protect that layer to not dissolve. The one thing that we discussed a few classes ago. But you don't want to have a lot of them. So there is a some amount hardness is needed, but not too much. If you have too much, this is a risk. So again, the only concept you have to remember is everything positively charged, 2 plus or 3 plus charge. Higher charge are not very common, so always we write 2 and 3. And I gave you example everything I can think of, all these ions. And monovalent ions do not contribute to hardness because they are too soluble. They are not going to make this kind of foam precipitate. And there is another real life consequence where it come from. If you think of where the calcium, magnesium come from, it's come from the rock, the aquifer materials. There are some location you can see the sinkhole, this form like this, how it forms. Well, that's the reason. If you think of many of the salt, let's say calcite, calcium carbonate, magnesium carbonate, they are extremely soluble when you are adding them in acid, strong acid, or weak acid, or anytime you increase the pH or decrease the pH, which is acidic. And how the pH increases? Well, when you have acidic rain, CO2 or NO2, SO2, these kind of gas are there, and when they dissolve, they create acid. SO2 create some S2SO4, sulfuric acid. CO2 create S2CO3, carbonic acid. NO2 create nitric acid. Okay. So now you are basically pouring this acid on the soil, and when you're pouring acid, this will form this SCO3, because the soil can dissolve SCO3. This will become SCO3 minus plus H plus. So that's the acid. And this one will bind with calcium carbonate, the calcium, and it will dissolve as calcium carbon. And calcium bicarbonate is soluble. It is not solid. So that means you are dissolving away this calcium carbonate from the aquifer or the soil. So the rainwater, as it percolates, it's kind of dissolve all these um, the rocks. So after a point, you didn't even realize that being dissolved away beneath your feet, and that's how the sinkhole are formed. When the sinkhole form, these are the things where you find high concentrations in groundwater, and that's the source of hard water because it has lots of calcium and magnesium. So this is something naturally happens, not like we pollute it. If you are living in an area which has lots of limestone, you will have hard water. So that means you have to remove this calcium and magnesium. And as I said, this is something important for you to know how much hardness you have. So when you ask the water distribution company, they'll give you what's the hardness. And usually this is the unit. Uh, Most of the time, because the source of hardness is limestone, calcium carbonate, which is very common, a lot of time people report it as calcium carbonate as opposed to moles per liters or milliequivalent per liter. So a lot of times you see the units are as calcium carbonate. Okay, we'll get to that why it is useful to do. Because when you remove hardness, you are removing as calcium carbonate. Engineers want to know how much of the stuff you are producing, how much weight of the stuff that I have to remove from treatment facility. So if you know calcium carbonate weight, then it's easier to calculate that value. Because calcium is very common, most of the hardness is because of calcium. That's why they always convert everything as a function of calcium carbonate. So the unit is as calcium carbonate. So soft water is less than 17.1. Slightly hard water is between 60. Moderately hard is between 120, 60 to 120. hard water is 120 to 180. So most of the time you don't have to do any treatments. In fact, if it is less than 17.1, it's not actually a good thing, because if it's too soft water, your scale will not form. And if the scale doesn't form, it might also corrode. So that's why this is also a corrosion prevention. So if you have too soft water, they add some of the hardness by adding calcium or magnesium. But if you have this much range, then usually they don't do any treatments, because that's normal, that's okay. Once it get to this level, you have to treat them. Again, let's see if we learn the hardness concept. I'm going to start a poll again. In winter, sodium chloride is added as a road salt, which can dissolve in water from snow melt and increase the salinity of water bodies. Would it increase the hardness of water bodies? You're adding sodium chloride, okay? So again, it dissolves. Now I ask you, does it change the hardness? Does it increase or decrease? I'm just saying, is it changing or not? Yes or no? Again, think of what is the hardness definitions. I'm going to go back the very first slide I talk about. Hardness is everything 2 plus charge or higher. Okay. Okay, I'm going to end the poll so that we can continue the conversation. So to share the results, 77% says no, and 23% says yes. Okay, let's think of what does that mean. So hardness is again emitting any positively charged ion. Concentrations of calcium, magnesium, irons, these are all positive charges. Okay, these are most common ions. You can keep adding more. Strontium, there are so many things you could add, but these are more common. Calcium, magnesiums are more common. You don't have much irons because they are not very soluble. They will dissolve. These are in high concentration. So you can ignore all this most of the time if you're looking for hardness. Um, so now question is, are you adding any of these ions? As you see, you are adding only sodium plus. That's the only positive charge you are adding. But that's not 2 plus charge, that's just 1 plus charge. So as I said, monovalent ions, as written here, monovalent ion doesn't contribute to hardness, okay, because they don't have affinity for carbonate to create salt. So that means the answer is no. All right, so now that you know the concept, let's solve some questions, because this is all about solving again and again, that we will learn a lot more. So again, I just want to say that unit of hardness is milligram per liter as calcium carbonate, because they are interested in how much solid you have to deal with after you precipitate out those calcium or magnesium. So they have to express as a mass, not as a moles, because they don't understand what is mole means. If you say 1 tons of stuff you have to deal with, you can manage it. So now let's see, how do you convert concentration of any species, because you might have a lot of different species. If I say you have, let's say, 2 milligram per liter of iron, just throwing a number here, okay? And so I say how much that iron concentration is as milligram per liter as calcium carbonate. That's what I'm asking. And you already did that in the very first class, how to change one unit to another unit. We'll just go over again. We are applying the same concept here. So you just have to know the mill equivalents, or what is the molecular weight and what's the equivalent weight. So that's the answer is this: milligram per liter of any substance. Let's say, I'm just saying iron because I just talked about it. Is so you have 2 milligram iron, and you want to say how much that is as calcium carbonate. So that means you are saying this one is you have 2 milligram of iron in 1 liter of water. Okay, I'm saying how much equivalent of calcium carbonate would have been present if you take account for the reactivity. So what you have to do is, um, I'm not going to change milligram to gram, gram to moles, all that stuff. So let's think of let's write it so that you know all the steps. So let me take it back. 100 milligram of anything, 1000 milligram is 1 gram of anything. Okay. Then if you think of what's the molecular weight of iron, because you have to change to a carbonate. First you have to mass milligram, you go to gram, then gram to molecular weight, then molecular weight of, and then you go to molecular weight of B by using the equivalence. How much equivalence of charge or N, and then you go to gram of B, then that goes to milligram of B. Okay, that's how you change. That's all I'm changing. So molecular weight of iron. So I'm just going to write molecular weight of iron. That's in gram. Okay, is 1 mole of iron, and 1 mole of iron has 2 charges because I say iron 2 plus charge, and you know that calcium carbonate CO2 plus CO3 2 minus, so it has also 2 minus charge or 2 plus charge. So they are also same amount. So 1 mole of iron is 2 normal iron. Okay, and 1 normal iron is same as 1 normal or equivalence of calcium carbonate because they have the same charge. So I'm just writing here CaCO3, and then you go back again. So the same way. So if I remove all these step and step, all you have to remember is this. Look at this one, molecular weight of calcium carbonate divided by the equivalence of calcium carbonate, molecular weight of the species that you want to calculate. So that would be milligram per liter of A times equivalent weight of CaCO3 divided by equivalent weight of iron. Okay, so that's all you are trying to do. So we'll do multiple examples so that you see that one. So now question is, this equivalent weight is always, this N value is important. You have to know what is that N value. Usually that's the number of charge. Okay, so look for positive or negative, doesn't matter. That means it's reactivity is based on the charge. So I just gave you this table where you can determine the equivalent, the charge is N. Usually it's a 3 plus charge, so N equal to 3. If you're looking for, let's say, um, sodium, that's 1 charge, so that's why N equal to 1. So if your molecular weight is 23 divided 1, equivalent weight would be 23. Let's say calcium. Calcium is plus 2 charge, molecular weight is 40, and number of charge is 2, or so that means the equivalent weight is 20 because you have 2 charge. So for 1 charge is around 20 gram. This is milligram per milliequivalent. So same thing, everything you can look for that. So it's very easy to do that one if you have a charge, like negative charge, so just divide molecular weight by the same charge, so it will not change. If you have 3 charge, 3, so then you divide 95 divided by 3, this become 31. So this is 95 divided by 3. Okay, just example. But if you have a neutral, that's where you have to break them down first before you realize what charge it is. So as you see, all of them has 2 plus charge or 2 minus or 2 charge. So you might wonder how carbon dioxide become 2 charge because it doesn't have any charge. Well, you have to think of this is all the reaction is happening inside water. So carbon dioxide doesn't stay as carbon dioxide as a gas in water. In fact, it reacts with water and it become carbonic acid. Okay, so when I write this one, this is actually carbon dioxide, dissolved carbon dioxide in water. Okay, so this is dissolved CO2. That's another way to write it because you are combining water with a CO2. And same thing, magnesium. So that means it has 2 plus charge here. If you break it down, it has CO3 2 minus and 2H plus. So that means there are 2 charge here. That's why there is a 2 here. And if you think of calcium carbonate, it's the same reason. You have a carbonate, that's a 2 charge, because it will not stay as calcium carbonate neutral. The reactivity is based on the charge it becomes after it dissolves. The same one here. So it becomes Mg2 plus 2H minus. So whether you look at positive charge or negative charge, you already get that 2 charge because it has 1 negative charge. So that means total 2. So again, these are all the things you can think of. There is no other species you ever want to deal with it. So every time you are solving this kind of question, if you have a species given here, you can calculate this number. Okay, just look at the molecular weight and calculate the n. That way you can convert that concentrations to calcium carbonate concentrations. Why this table is important? Because all the time you have to convert everything as calcium carbonate, and you will be using this formula. This formula.
Professor, for the other slide, the I think it's slide 16.
Okay.
Yeah. That one. Does A does that mean like a compound or like an
Yeah,
element?
any compound. Here, for
Okay.
example, I ask iron. Okay.
Thank you.
So A could be anything here. So this is A. So I'm asking, what is the concentration of aluminum as calcium carbonate? So that A is aluminum. So we'll have a lot of examples. So again, this is the unit you want to calculate. So milligram per liter of anything. Okay. If you want to convert them as calcium carbonate, this is what you have to do. As I said, all I did is write the formula. N of calcium carbonate is 2. So this is 50 gram per equivalent. So all you have to do is equivalent weight of that A. And whatever the concentration, this is given. Usually given aluminum concentration or iron concentration is given to you. You have to change to as calcium carbonate. Okay, as CaCO3. And so all you have to look for is equivalent weight of that species. So that's given here. Okay, that's 9 gram, all that stuff. So if you have, so let's solve one example. That way it's easy to know. There are 3 examples in fact here. So for instance, the number 1, I ask you the calcium concentration is 120 milligram per liter, but you have to change that to as calcium carbonate. So again, the unit is 120 milligram per liter calcium times equivalent weight of calcium carbonate, equivalent weight of CaCO3 by equivalent weight of Ca2 plus. Okay, so let's write that one. 120 milligram per liter. Equivalent weight of calcium carbonate is 50. All the time we write that one. So for instance here, just to show 50. It doesn't matter what unit you write because it cancel out. You have to write the same unit. And calcium equivalent weight, look at the calcium. Molecular weight 40.1 divided by 2. So that will be 20. So it's a 20.05, but it's rounded up. So that means this would be 120 times 50 divided by 20. So that's 26, 6 times 5. So that will be 300 milligram as CaCO3 per liter. Okay. So what that means is if you have 120 milligrams of calcium, you are going to produce, you have to deal with 300 milligram of calcium carbonate when you treat that hardness. So that's how they correlate everything. So now let's do the same thing for magnesium. I'm just going to quickly I'll remove some of the steps. All I have to write is this is 50 gram, that's calcium carbonate. Look at the magnesium equivalent weight. So molecular weight is, or the atomic weight is 24.3 divided by 2 because per charge, so that's 12.2. So you can find whatever that number, it will be as milligram per liter as CaCO3. Let's do the same thing for sodium. Again, 46 milligram per liter times 50 gram, that's calcium carbonate, because that's what we are trying to convert, divided by sodium. Sodium has one charge, so that should not change the molecular weight. So sodium 23, 1, it become the same. Equivalent weight is same as molecular weight or atomic weight. Again, all you are doing is converting one unit to another, which you learned in the first class. So that's nothing different. You are now applying everything to just mass balance. So this is the mass balance. Always we have to ask what is the hardness. A lot of times you are asked, um, um, a lot of time you are asked to calculate total hardness, carbonate hardness, and non-carbonate hardness. There are some questions on chart window. Isn't equivalent weight on the chart given in milligram? Um, okay, let's see. So you see here, what is given is milligram per milliequivalent. So what it's saying is equivalent weight is in a gram. So one equivalent weight of aluminum is, let's say, 9. So that means one equivalent of aluminum is 9 gram. But 1 milli equivalent should be 9 divided by 1000, because milli is 1000. So when you divide 9 gram by 1000, it becomes 9 milligram. So this is milligram per milli equivalent. So same thing as gram per equivalent, because they're the same units. Okay, so many of your long question, you will be asked to calculate total hardness, carbonate hardness, non-carbonate hardness. So you have to just understand the concept before you answer this question, because this is just adding up number. So once you have actual number, you just add it up. This is the equations. So let's write what is total hardness. Again, total hardness is sum of every ions that has 2 plus charge, 2 or more charge. So usually you can add everything here, but for all practical purpose, these are negligible. Okay, I wrote 3 dot because I want to say that in some cases you might have higher concentration of ions, but those are very rare. So in all practical purpose, you can neglect all of them, because the solubility of those ions are very small compared to calcium or magnesium. So for all practical purpose, if I ask you what is the total hardness, all you have to do is, you know the concentration of calcium, you know the concentration of magnesium, just add them up. And again, just to give you a hint here, you do not add them if it is milligram per liter, because they are not same unit. Calcium weighs different than magnesium. You have to change both unit to same unit. Either you put as equivalents, which is normality, or you change it to milligram per liter as calcium carbonate. And we did all these calculations so that we can change to milligram per liter as calcium carbonate. So this unit will be milligram per liter as CaCO3. Okay, this is just one way to calculate. So first convert to calcium concentrations, because usually given that milligram per liter, convert to calcium carbonate, then you do that one. So that's easy. Let's think of what is carbonate hardness. Carbonate hardness is, you are saying this calcium can come from many different sources. So how many of those calcium is coming from carbonate source? If you think of the original example over here, I'm just asking, is this calcium coming from this source? Because there are other kind of salt. There could be magnesium, let's say magnesium sulfate. That also can give you magnesium, but they are not coming from carbonate source. That's why you are saying, when I ask what is the carbonate hardness, I'm just asking you to sum these two. Okay, any calcium coming from as bicarbonate. So that's why if I write the equations, I wrote it here. Carbonate hardness means any calcium that coming from the salt of carbonate. Anything that is not coming from salt or carbonate is non-carbonate hardness. So that means this calcium magnesium could be coming from CaSO4. This could be magnesium chloride or calcium chloride, all those things. Okay, I just give you a couple of examples. Okay, any non-carbonate ions can also form the salt. So again, total hardness is just sum of all calcium, magnesium. Carbonate, non-carbonate hardness is all about where that calcium came from. Is this coming from a salt of carbonate, or is salt from non-carbonate species. That's all. And always total hardness is same as carbonate hardness plus non-carbonate hardness. Okay. So once you know this concept, we can solve any questions. Okay. So let's start example. Couple of things you have to see. Graphically, it's very easy to understand. So let's think of what is total hardness means. When you do like a scale, arrange them together, total hardness, because they are all same unit, you can add them together. Total hardness is calcium plus magnesium. Okay. You take all calcium, you take all magnesium, that become total hardness. What is carbonate hardness? Means the fraction of that calcium magnesium is coming from SCO3 source. So if you know how much SCO3 in your solutions, then you know the carbonate hardness. Why I didn't write CO3 2 minus? The reason, as I said, if you remember few slides back, concentration of SCO3 typically at the pH range is much higher than other. So you can neglect all the other. So that means carbonate hardness can be equal to amount of SCO3 present in the solutions. Assuming this SCO3 is less than, assuming SCO3, because if the way I write here, all the bicarbonate is can be consumed by this calcium or magnesium. There will be still some magnesium calcium left. So you don't have sufficient SCO3 to coming from as calcium and magnesium. That means if you account for all SCO3 and you still have some calcium magnesium remaining, what you are saying is those calcium and magnesium might have come from other salt of non-carbonate species. So that's why non-carbonate hardness. So that's why, for instance, here we call that chlorine. Okay. So that's all we are writing here. So if you sum it all, calcium and magnesium, that become total hardness. So this, all these things is total hardness. And this one is carbonate hardness, because you are saying these must be from this salt, and this is N. But now question is, this is true all the time? Does it mean that non-carbonate hardness is always equal to amount of SCO3? It may not be true, because there may be some NaCO3. If you add this one, you're adding SCO3, but you're not contributing to hardness. So that means you have to always compare how much carbonate you have. And I gave you another example like that. So here, if you see, you have calcium, you have magnesium, you have some sodium, and you have all of them are SCO3. That means all these calcium, magnesium, and sodium are bound with carbonate. There is no extra ions remaining to account for. So that means you can say here there is no magnesium and calcium remaining, which is coming from other source, non-carbonate source. So that means here you can say this is total hardness is always the true, calcium plus magnesium, that's total hardness, and carbonate hardness is only this much, because even you have lots of bicarbonate, they are not all contributing magnesium or calcium. Okay, so I gave you this, this, we'll do some examples so that you can know, but this is the formula you have to remember and the concept I just explained. First, look at SCO3. If it is less than total hardness, that means carbonate hardness is all SCO3, and non-carbonate hardness is the remaining amount. But if your SCO3 is exceeding the total hardness, that means there are some SCO3 bound with some non-carbonate, ions like sodiums. So again, this is all confusing a little bit to some extent. Let's solve example that's why I said there are many examples. So we learn everything about hardness now. So let's solve many examples so that you know how to do it. Given the following analysis of groundwater at pH 7.6, this is very important. Why that number is given? You are not going to use it at all. All it's saying is at that pH, this pH is below 5 to 8, right? Within that. So that means you can ignore every other carbonate species. You can say alkalinity equal to SCO3 That's all it means. Okay, so if you are given SCO3, which is the case, you can assume that everything is a SCO3 is alkalinity. That's all it's saying. Sometimes I would not give SCO3, but I will give you just the alkalinity. That means you can equate that together. That's all it means. Just look for the pH. Construct a bar chart of constituents with the concentration given in milligram per liter as calcium carbonate. So it already calculates for you. It calculates the molecular weight, it calculates the equivalents, and it calculates the concentrations. It calculates the concentration of all that as calcium carbonate. So everything is already done. You don't have to do calculations. But in reality, in the exams, you will be given only this much. And these are all constant. These are all known from the table, so you can always calculate that here. But here it's already done. So let's solve the that graph. So first, let's calculate the total hardness. Total hardness is, as I said, combination of positively charged ions, positive with 2 plus or 2 or greater charge. So what are the hardness that contribute? So total hardness is everything that has 2 plus charge, 2 plus or higher. So we have your calcium, you have your magnesium. Usually that's where it's supposed to end, but in this particular case, they also give you iron. So you cannot discount that, because usually you can neglect it, but still there is small amount is given in this particular case. You're not adding sodium because that doesn't contribute to hardness. So let's draw that one. I'm going to draw a scale. So if you add them together, it will be 375 plus 60 plus 3.2. What that number would be? 0.2, 8, then 6, 438.2 milligram per liter as calcium carbonate. Let's calculate the, now the question is the total hardness more than SCO3? Because that way you want to know where they're coming from. So SCO3 amount is 450. What does that mean here? It means total hardness is less than amount of SCO3 present. All that saying is all these iron, calcium, magnesium, iron, they're all associated with carbonate, because you are just have sufficient amount of carbonate present to create that salt. So if that's the case, based on the equations, that means there is, if all the hardness is accounted by carbonate, there is no non-carbonate hardness. So that means non-carbonate hardness equal to 0. What I'm saying is all carbonate is taking up all these ions. There is no other ions remaining to take any of the hardness ions. Okay, so let's solve it. Let's do all.
Professor?
Yes.
The concentration of bicarbonate should be 69, not 450. Not 450.
So, oh, you're right. I made a big mistake. Thank you. I was looking for a different column here. Okay, here it is actually 369. That completely changed the answer. I was going in the wrong directions, because you have to compare the right units. So this is milligram per liter. So this is let's say 438. So that means you are saying out of 438, 369 are accounted by carbonate. Everything else must be some other ion. In this case, it's given chloride. So that means you can say here pH is greater than SCO3. So that means carbonate hardness should be equal to SCO3, is given already, 369. And non-carbonate hardness, maybe the difference. So total hardness minus SCO3, which is carbonate hardness, should be 438.2 minus 369. So that would be 2, 9. This will be 6. Yeah. Okay. So you can calculate all that by this way. Okay, we calculate everything. So now let's plot it in a like how we should plot, because I ask you to make a bar chart. So the way to do it
Professor,
is, yeah,
for the total hardness, why did you add the iron? The iron 3 plus?
I added it, didn't
No,
I?
yeah, but why? Like I'm not sure why you added the.
Okay. So as I said, total carbonate or total hardness is everything that has 2 plus charge, 2 plus or more. So
Oh,
like here, everything you have to account for as long as they are present. But most of the time, this, as I said, you can neglect everything else if they are very small concentration. But here it is given to you, so you can't ignore it.
okay. Thank you. Yeah, I thought we were supposed to ignore it, but okay.
Yeah,
Now I- thank
if
you.
it is given, you have to keep it. If it's not given, you can't. Okay, you can assume this is 0.
Right. Thank you.
Okay, so let's draw the graph. So basically, you have to have a scale. Um, so the scale is around 438. That's what. Let's say I'm going to make the scale here 450. So 50, 100, 150, 200, then 250, 300, 350, 400, 450. Okay, 450. That way I can account for all this. So I'm just creating a drawing a map. Okay. So let's write calcium. Always you go from calcium, magnesium, then everything else. So let's draw calcium. So I'm going to make the color. Let's say I'm going to make calcium as pink. So how much calcium you have? 375. So I'm going to go all the way 375. So this is 300, 350, 375. Okay. This is 375. Then you have another 60. 375 plus 60 is how much? That would be 25, 25. So that would be 35, 435. So I'm going to make, see, I'll make this color as calcium. So that will go to 435. So 450 here. So let's say this is going to go to, this is 375 border. This is 435 because I'm adding the 60. And then the rest one is going to be, let's say this is the iron. Okay. So this is again, this is Ca2 plus, this is magnesium 2 plus, and this is iron. So account for all of them together. And now we have to account for SCO3. SCO3 is 369. So it will go to around 369. So I have to think of where 369 will be. This is 375. Oh no, this is a 350. This is 375. So 369 will be somewhere here. Okay. I'm just randomly picking a number because I can't. So let's make a color for this. Let's make a color for this one. So, okay. So that's the amount is 369. So this is SCO3. Okay. And then the rest of them must be coming from chlorine because there has to be something else. So I have to add chlorine. 369. Chlorine is how much amount? 284. So let's make 284. So I'm just going to add 284. Let's make a color for this one here, yellow color. So 369 for 284 is how much? 369 plus 284. I have to calculate. I didn't. 3.
It's 653.
Thank you. All right, 653. So I didn't have account for 653, but let me do this way. So that way you can see that this is going to go to all the way to whatever that number is. Okay, so 653 all the way. So what does that means? All this carbonate up to here is calcium bicarbonate. Then you have some extra carbonate that become calcium chloride. Then rest of the magnesium is, this is chloride, okay? So that means this much amount is calcium chloride because you are already done with all the carbonate by the time you reach there. And then rest of the magnesium must be coming from magnesium chloride. This is magnesium chloride. And then this is iron chloride. And you have also something left over here. This one. I could not find any other color yet. So let me see. Maybe I'm going to pick a color here, blue. Okay. So that means this amount must be coming from sodium. Okay, because although they are not accounted for carbonate hardness. So that's all. So this is how you are going to solve by making example of. So this is all the way here is total hardness, and only this much is carbonate hardness, and the remaining amount is non-carbonate hardness. Okay. So when you do multiple time, you'll get to know this one. This is just adding up together. So I gave you multiple examples. Let's solve one more example. Here I gave you already the unit, so you got to do it again. So let me draw the scale. Then you should help me how to do it. That way you all learn. The scale here is total hardness is these two together, added together. So 175 plus 75 is how much? 250. Okay. And if you think of all the negative ions, that's also 250. So they're all matching. They should all add up together, same amount. So when you write calcium, let's do this one. So your scale is around 250. I'm going to do 50, 100, 150, 200, 250. I'm just throwing a way to calculate. So let's draw the calcium. Always you start with calcium, then magnesium, then everything else. And then, so this is, the sequence will be always that because calcium is more easy to dissolve. So then this is 1, 2, in that order from left to right. Okay, let's solve this one. I'm going to do the calcium. I don't know what color I want. Let's say calcium is pink. Calcium is pink. And 175. So go from 0 to all the way 175. So that's in between, halfway. Okay. 175. And then another 75 is all. I'm going to pick green color. So this is 250. So that's all the way 250. So that means this is calcium, which is equal to 175. This is magnesium, which is equal to 75. So that's why it add up to 250. Now let's do the carbonate. SCO3 is 200. So I'm going to do SCO3. Let's say this color is SCO3, 200. So you go all the way to 200. Okay, that's roughly. And the rest amount must be chlorine, 50. So I'm going to pick another color. So what color I didn't pick? This one. Okay. So this is 200 mark. This is 250 mark. And so this is chloride, which is around 50, and this is SCO3. Okay. So now that you all done it, so let's visually write what is total hardness. Total hardness is always calcium plus magnesium. Any other ion is not present, so I'm going to write that one. So total hardness is all the way everything. Okay, because calcium plus magnesium, I add it up together, so it's all here. Let's do the non-carbonate hardness or carbonate hardness. Here, some of the, you see this total hardness is always more than carbonate or the bicarbonate present, so that must be your non or carbonate hardness, and the rest of them must be non-carbonate hardness. So now you have to write all the different species. What could be the species SCO3 here? So that means if I write all this thing, let's break it down here. So this much, you have calcium is there, you have so much, so this amount would be CaHCO3. Because this is 1 minus, so there will be 2 charge here. So that's because you are, this is SCO3 and this much calcium. So that means all the SCO3 before that is all part of calcium, coming from calcium. Then there are still some SCO3 remaining, this much amount. That extra SCO3 is must be going to magnesium. So that means this amount is magnesium SCO3. And then you account for all this magnesium. That means now you are done with all the carbonate. So where the rest of the magnesium goes to, that means this goes to the chloride. So this is MgCl2. So what you are saying is all the carbonate hardness come from, some part come from calcium carbonate hardness, bicarbonate, some come from magnesium bicarbonate, some come from magnesium chloride. You are just matching the positive with negative ions. Okay, so now I want you guys to do this one. I'll give you time to do it. So I am not going to, you guys tell me how to do this one. I'm going to just draw the scale and then you tell me. Again, this is 175 plus 75. That's the total amount. Positive charge or not total amount, 175. Total positive charge is 175 plus 75 plus 25. So that will be 275 if you add them together. So my scale is all the way 275. So let's say this is 100, 200, 300. And then 50, 170, 275. This is 275. Okay, so tell me which one I should draw first. Let's draw the positive first. Which one you will draw?
Calcium.
Yeah, go ahead. Calcium. Okay, let me.
Up to 175.
Okay, let's draw that one. Calcium, I'm going to change the color now. So this is this color. So 175. So let's see where is 175. So this is 150, 175. Okay, so I have to draw all the way here. So let's draw calcium. Next, what?
Magnesium.
Magnesium. So you'll just add up on top of that. So how much magnesium is 75? So 175 plus 75. Where this will end?
250.
250. So where is 250 here? So this is 250, right? This is 250. So we got to draw that one up to there. So I'm going to change the color. That's magnesium. Okay. It's good. So let's do the sodium one. Where to end? Another 25. So 250 plus that value. So I'm going to pick a color. We already picked these two colors. So let's pick another one. So that's, let's say, sodium. So that's going to be 275 here. Okay. So that is sodium. Okay. So we are done with the positive ion. So somebody, other person can help SCO3. It goes from 275. So that means you start 0 here. This is like this is straightforward. So I'm just going to write here. So this is all the way to 275. Okay, because that's all. So this is SCO3. Now you got to tell me what is total hardness. What's the total hardness?
250.
250, because you just add them together. So visually, you go all the way to 250. So this is total hardness. What is the non-carbonate hardness? Or what is
There
the
is none.
carbonate hardness?
It's all carbonate hardness.
Yes, because if you see, the total hardness is up to here, and you can account for all of them by this number because it's always all there. So this is also carbonate hardness. Okay, because all the magnesium, calcium can be accounted as SCO3. You just have way too much SCO3. And so what is non-carbonate hardness? How much of the calcium, magnesium coming from source other than carbonate?
None.
None. So that means there is nothing, because everything account for SCO. So NCH is equal to 0. So already you have known. So calcium per magnesium, if you see this one, this is 250. Carbonate hardness is 250 is 0. Okay. All right. So I'm not going to solve example 4. Do it on your own, or I'm going to record it if you don't know how to do it, because this is all something given. Again, it says, what is the alkalinity? I'm just going to write it here because the pH is near neutral, means 7. When pH is around that, the alkalinity is equal to SCO3. Okay, that's all it means. That you can assume that one. What is the total dissolved solid concentrations? What is that total dissolved means? You are adding up all together. Total dissolved solid is calcium plus magnesium plus sodium plus every ion possible present here. SCO3 plus SO4 plus chlorine. Okay, you're adding them all together. As long as you are adding the same unit, it's fine. So that's all it means there. Draw an ion concentration bar graph. I did it already. So this is ion concentration bar graph. Okay, so if you go back here, what that means here, this is sodium. So this sodium must be present as this much is NaHCO3. This much is CaHCO3, because this is calcium carbonate. This is MgHCO3. As I said, so this is just a different ion species. Okay, so you should be able to do it again. I gave you another example. I mean, you can just put all the value and do it. I gave you another example. You can also do the same thing. It's just adding up together. So I solved 2 questions. You should be able to do that. I give you another. Again, this TA will go through this process, these questions if you don't know. This is a fun exercise to do because you are just drawing. So I'll recommend doing this one. If you have difficulty, let me know on CampusWare so that I can record it separately. But as far as I have already solved 2 or 3 examples, so there's no point of solving those. The last one is softening, is about calculating how much amount of stop you need to add to remove this calcium and magnesium. This is again the same stuff that we learned. It's just about mass balance calculating. You just have to know how to remove calcium, magnesium. It's a very simple concept. Then you just have to do the math. And the only concept you have to remember is this. You can remove calcium by precipitating as calcium carbonate. You can remove magnesium by precipitating as magnesium hydroxide. The reason is the solubility of this species is very low. So that means it's very easy to precipitate calcium as calcium carbonate, not calcium bicarbonate. Okay, so that means you have to add lots of carbonate, or you have to create lots of carbonate to remove calcium. So that means you have to supply this one. Same thing, you have to remove magnesium. It turned out magnesium carbonate is very soluble, so you're not going to precipitate out. It turned out magnesium can be precipitated by hydroxide. So if you want to remove magnesium, what do you have to do? Add lots of OH ions. Add OH to remove magnesium, and add CO3 to minus to remove calcium. That's the only way. So imagine you're taking shower in this hard water, and the company says that you can treat at your home. All you have to look for is how to get this SCO3 or OH ions. So any salt that can give you OH will be able to help you solve this one. It turned out you look for materials that's very cheap or cheaper way to find those two materials, then you can add those. So that's all about engineering. So now question is, as I said, source of OH in nature is calcium hydroxide. The reason is it's actually lime. It's a CaO. That's the rock that you get, lime. And when you mix with water, it becomes CaOH. So if you want to add OH, you look for this lime slurry. Now here is the interesting fact. Your goal is to remove magnesium, and what you are doing here, you are adding OH as a form of calcium hydroxide. But you are removing magnesium, but you are also adding calcium. Calcium also causes hardness. So that means you are removing magnesium, but you are in the cost of adding calcium. That means you have to remove those calcium separately. Now question is how to remove calcium. As you see, calcium can be removed by carbonate. And this carbonate usually naturally present in water as alkalinity. So you don't have to add anything. But sometimes if you don't have enough of this, you have to add carbon dioxide so that it creates carbonate ions. The issue here is that it's not straightforward. You cannot add carbonate because every carbonate you add, if your pH is within that range, it becomes SCO3, and SCO3 is not going to precipitate calcium. So for this reaction to happen, you have to make carbonates stable, and that carbonate is stable at the pH in this range. If you see, this is stable after pH 10.3. So this reaction can occur if pH is greater than 10.3, because at that position carbonate is, this is 10.3 here, okay. At that pH your carbonate is can present as carbonate, not as bicarbonate. So how do you increase the pH? Increase pH by adding OH ions. So that's how people do. People do first calcium, they add calcium hydroxide so that the pH is rise over 10.3 because of all these OH ions. And then once the pH is so high, any bicarbonate is there, become carbonate. And those carbonate now precipitate as calcium carbonate. So entire operation depends on raising the pH by adding lime and then precipitating calcium and magnesium as this salt. And sometimes if you don't have any calcium, or let's say there are some calcium left that you do not want to precipitate as calcium carbonate, let's say there are some calcium left, you cannot add CaOH multiple times because you are adding and you are removing the same thing. So at that time you can add CO3 from a different source. So that is Na2CO3. So that means if you are adding from this source, you are not adding any more hardness because you are adding CO3, but you are adding sodium. Sodium doesn't contribute to hardness. So that means this calcium can be precipitated out. So that's the concept. So if you think of design, that's exactly what they design for. So if you go to any wastewater treatment plant, so the very first thing they do is they add lime slurry. So this is CaOH2. The goal of CaOH2 is to increase the pH. First, it increases the pH, and also that OH will also precipitate out any magnesium. Okay. So as the pH increases, any CO3 present in the solutions will precipitate as CaCO3. and any magnesium present and precipitate as magnesium OH. So that's the reason they do this one. COH increase the pH as well as precipitate magnesium. But now, because you precipitate out all the carbonate, there are not enough carbonate remaining. You have to add more carbonate for them to precipitate again. So that's why they have to inject carbon dioxide. So this CO2 they inject to make the pH goes lower, because you added so much base that the pH is extremely high, and also to increase the CO3 concentrations, because you are precipitating them out, they are required. So once you finish that one, you add soda ash. Soda ash is Na2CO3, because you have got rid of all magnesium. Right now you have some calcium left because you added this calcium. There will be some calcium, and that place you add sodium carbonate with the calcium. This calcium will precipitate as calcium carbonate. So that's the reaction. First you add calcium hydroxide, then you add sodium carbonate, and the carbonate this SCO3 or CO3 already present in water. You don't have to do anything else. And sometimes to change the pH, you dissolve carbon dioxides. So that's the operation, that's the theory and the chemistry behind it. And so to calculate how much amount of calcium hydroxide you have to add, the reason is why you are adding this, because this is cheap. The reason why you are not adding, because you're saying, you can say, why not add sodium hydroxide? Because then you are not adding any more hardness to remove hardness. Well, you can do that one, but sodium hydroxide is way more expensive than lime. Lime is way so cheaper, so that means you can add those. The cost will be a lot less. So that's why people prefer calcium hydroxide, because this is cheap. Okay, but if you think of chemistry, if they are all same if they are all same cost, then you would have add sodium. And then you add when you add lime, it can also consume some of the OH will be consumed by carbon dioxide, because carbon dioxide, as I say, in water is S2CO3. So is S2CO3. So that's basically based on the pH. Let's write the extreme pH. So that means it has 2H plus charge. So any OH you add here, that will be consumed. Some of the OH will consume by this carbon dioxide, because it has this 2 plus charge. So that means even though you are adding lime, not all OH is going to go to magnesium. Some of them will be consumed by carbon dioxide, and the rest of amount will go to magnesium. So if you think of the OH you added, this will go to CO2, and some of them will go to magnesium. The rest of them will go to magnesium and precipitate them as magnesium OH2. So again, these are all different chemical reactions, so it might be overwhelming. Go step by step, because it's something you'll do many exercise, then you'll able to understand chemically. But for solving the problem, you don't have to remember any of them. The equation is given, just plug the value, get the answer. So I'm just going through the concept here. So that's all. I wrote all the equation here. Carbon dioxide, when you are, if you know the carbon dioxide concentration, you have to know how much lime will be consumed because of carbon dioxide. So this equation derived that one. So that means if you have some amount of 1 mole of carbon dioxide, you need 1 mole of calcium hydroxide. As I said, this calcium hydroxide will precipitate. What it does, it makes precipitate calcium carbonate, because it increases the pH. So that increase the pH will precipitate this out. So you will have you will know how much calcium hydroxide is needed to precipitate out this much carbonate hardness of calcium. Same thing for magnesium hardness, magnesium carbonate hardness. You need also calcium hydroxide, lime. That reaction says it. So the key thing here is 2. For 1 moles of magnesium bicarbonate, you need 2 moles of calcium hydroxide. So when you do mass balance, you will have to account for that twice amount. And then remaining calcium, which is non-carbonate hardness, these are carbonate hardness. I'm just going to write the short form so it's easier because we have been writing that. Non-carbonate hardness. So this calcium magnesium is from non-carbonate hardness. Okay, something like sulfate or chloride. To remove them, you should add sodium carbonate, because if you add calcium hydroxide, you are replacing and you are also adding more. So you are adding sodium carbonate. For magnesium, you add this one, but you also you are adding this one, Na2CO3 together. First, you add calcium to replace magnesium as precipitated as hydroxide, and then the remaining calcium can be precipitated as carbonate. So this reaction is something you need to write in cheat sheet so that you know how much lime is required. And again, this is the reaction why this lime requirement is this. So this is all you have to know. Amount of lime required to treat your solution is because of carbon dioxide, because of carbonate hardness, because of magnesium hardness, and because of non-carbonate magnesium hardness, or another to say is Ca2 plus. Okay. So that's all the equations, and that equation coming from here. So as you see, the only thing you have to remember, I have a two term here. The reason is, for 1 mole of magnesium bicarbonate, you need 2 moles of calcium. So that means you are saying whatever amount of magnesium you have as non-carbonate hardness, multiply that times 2. So that's the reason. So once you know this is the total concentrations, that's as magnesium carbonate, you multiply that concentration to volume, you get the total amount of lime. So that's how the calculation is there. So same thing, how much this one is required is based on this equation. This is the only equation where you have bicarbonate are being used. So that means whatever the calcium or magnesium non-carbonate hardness amount is the amount of required for the this particular soda ash. So if I ask you any questions on this one, all you have to do is add this one, these two. These are non-carbonate hardness. And this is already you know how to calculate from the previous thing that we discussed. These are already given. This is given. This is calculated. If you remember, in all the equations that we we have been doing here, we have been calculating all this value. So once you know those value, plug those answers, you get the total amount. So again, this is it will take a while for you to understand different concept. I'm going to not try to solve it because we are out of time, but I'm going to solve that example after this class as a recording. But the 90% of the challenge is getting this number. Once you get this number, plot those graph, then you know specific values. And once you know the specific values, you put those in equations. If I ask you how much amount of this, you just plug the value, this value. So to solve this question, you should write these equations on your cheat sheet. Amount of lime equation is this, and these are equation is always you can calculate based on that graph. This is none. Okay, so this is also another example. This was in final 2018. We are running out of time, so what I'm going to do is I'm going to solve this one as a recording, in addition to some of the other questions that I didn't solve. That way you have an idea how to solve it. Again, you are just drawing the graph, putting the value, and just plugging those answers here. So this is the question is straightforward. You just have to, it will take a while for you to know why those equations are there. But for final or midterms, you don't have to remember why, because it's open book. Just have to plug the value and get the answers. But I encourage you to understand the concept. Read the textbook so that you know all the things that I discussed. Any question? And one thing I want to say, there are many questions I gave you to solve. And if you want to know all those equations, breakdown of the equation, how I come up with these equations, these are all given, because everything is added here, become something else, then they mix together to become this one. So only thing I gave you is this equation, but these are all the different steps. But you don't have to remember it. You just know that this is how this equation is become like this one because different ions are reacting. Other than that, I think if you think of this class, you have to remember a couple of things. What is alkalinity? What is hardness? How to estimate those based on that example I gave you. Once you estimate different species, everything else that to calculate is based on plugging the value and getting the answers. These values are you are estimating based on that bar graph, and you are calculating these concentrations. If you know this concentration, multiply to volume, it becomes the total amount of solid generated. So the most difficult part is coming up with that this graph. Which one? Let me show you. Yeah. As long as you know how to make this graph, everything else is much easier because you are just putting the equations and solving the answers. All right, so that's all about the hardness. So that conclude everything that you need to know before the midterm, which is on week 7. The reason we put the midterms on week 7 is because I want you guys to have at least 1 or 2 weeks of time to prepare for it. So everything we learn today is going to be in the part of midterms. We'll release the homework, and we gave you a lot of example questions, so you can solve those, and the homework is exactly same. So everything that we have example here is the homework question is exactly similar. So I don't think you should have difficulty in the exam, in the homework. If you do, obviously come to the TA office hour. So prepare for everything until this class for your midterms. Midterms will be on November 18th, 19th. One thing I want to clarify, the midterms is 24-hour window. That doesn't mean that you have 24 hours. It means that you can take exam any times within that 24 hours. So as soon as you open the midterm questions, you have 3 hours, or I'll look at now based on the question I said, is it 3 hours or 4 hours? But I'm not expecting more than 3 hours of time. So once you open the questions, then you start writing on your whatever page you have, and then scan it and upload on the Gradescope like you do for homework. The only difference is in homework you have 7 days or whatever time. Here you have 3 hours. So that means you have to prepare for each questions beforehand. And the questions are very similar to homework. I'm not asking questions which are very different that you have to think. It's already example questions before given. You just have to solve again. It will be mix up short question and long questions.
So you said
Professor.
they are through. Oh, I'm sorry. Did you say there are 3 questions in the midterm?
So in on Wednesday, I'll give you example question from last midterm, so that way you know how the format look like.
Thank you.
Professor,
Yeah.
for the in one of the slides you said between calcium and magnesium, one was NCH and one was CH.
Mm-hmm. Let's see. Yeah, let me go back. I think it can happen. So here. So if you see, all the calcium has to be accounted by carbonate. And then if there is any calcium left and you are running out of carbonate, then it has to accounted by other things. Okay. So in this case, calcium is 175 and your carbonate is all to 200. So this much amount must be calcium carbonate, bicarbonate. And the remaining amount here, you have magnesium and carbonate. But your magnesium is still there here. The rest of magnesium, that has to be magnesium chloride. So that's non-carbonate hardness. That means this is magnesium chloride.
I think it was on a few slides further.
Before?
No, further on.
Okay, let's see. Let me know where you, because I didn't solve any questions after that.
Oh, from here. It was the next one, I think. The next one. Maybe after this.
Okay, that's fine.
Okay, still further.
Okay,
Further. Further.
this
Yeah.
one?
Why
Yes.
did you say that's oh, you said both of them are.
Yeah, both are non-carbonate hardness.
Okay.
The reason is you remove all the carbonate hardness here. If you see the reaction term here, let's see the equation. Let's see all the equations. Okay, so this is carbon dioxide. So this you are using not because to remove hardness, but to remove carbon dioxide. You're adding this line to remove, this is carbonate hardness. So these two are carbonate hardness because I wrote as SCO3, right? But here I didn't write MCS SCO3 because that means what I'm saying here, this calcium may be coming from source other than carbonate. Same thing magnesium. So if you see the NaCO3 that is added, it's only added when you have these two equations. And those two equations are related to non-carbonate hardness.
Okay, got it. Thank you.
I would strongly suggest to read the textbook because, again, you are looking at a lot of information in one class. It takes a while. When you do this example multiple times, you will be able to get it. So don't worry if you still have some questions. Just ask on Piazza or not Piazza, Campusware, as well as on also in YouTube, below YouTube. But I will solve some of the questions so that at least I will solve one of these questions where the lime requirement, the final question that was on the final in 2018. I'll solve this one as a recording so that you know how I use it.
Okay, thank you.
Any other questions? I'm going to stop the recording now, unless you have questions. Stop share.